So welcome back, students, and here we are going to talk about now module 2 in strengths of acids and bases. Here in this module we are going to talk about factors affecting strength of bases and the various relations of pK and pKb. In the last module we have already discussed about the factors affecting strengths of acids. So let us go for the strength of bases. So generally, organic bases are the derivatives of ammonia, and they may be classified as aliphatic as well as aromatic amines. So, on the basis of the number of hydrogen atoms in ammonia replaced by alkyl group, we can classify amines as primary amines, secondary amines, tertiary amines, and this is aromatic amine, that is aniline. So what you'll find that in primary amines, one hydrogen is replaced by alkyl group. In secondary amine, two hydrogen atoms of ammonia are replaced by alkyl group. In tertiary, all three hydrogen atoms of ammonia are replaced by alkyl group. Whereas in aromatic amines, you have an aromatic ring attached to NH2 group. It's a primary amine. Now what you'll find that already we have discussed that in ammonia, nitrogen has this unshared pair of electrons which can be donated. Since it is electron donor, it is basic according to Lewis concept. Similarly, when I pass ammonia into water, it releases hydroxyl ion and therefore Arrhenius also says that it is alkaline in nature. As well as ammonia accepts proton and gets converted into ammonium cation. So it is a proton acceptor. Therefore, again, your Lorry-Bronsted theory, that is proton donor acceptor theory, will also say that ammonia is alkaline or basic in nature. When I replace now these hydrogen atoms by alkyl group, the electron donating capacity of this nitrogen increases and therefore the basic character should increase. Now there are various factors responsible to increase the basicity. Let us see one by one. The first one we are going to talk about is hybridization. So hybridization, as we know that carbon undergoes three types of hybridization. It can be sp3, sp2 and sp type of hybridization. The basic difference in hybridization of carbon changes its percentage of S character. sp3 hybridized carbon has 25% S character, whereas sp2 hybridized carbon has 33.33% S character. So in case of methylamine, that is CH3NH2, here NH2 is attached to sp3 carbon, whereas in case of aniline, it is attached to sp2 type of carbon atom. As the percentage of S character increases, the electron withdrawing capacity of that particular carbon increases, or we'll say that sp2 carbon is more electronegative as compared to sp3 carbon. Because it is more electronegative, the pair of electrons on nitrogen is more pulled by that particular carbon. In case of ammonia, in case of amines, that is primary amines, this particular pair of electron is pulled lesser as compared to in case of aromatic amines, and therefore aliphatic amines will be more basic as compared to aromatic amine, because the percentage of S character in aliphatic amines, nitrogen is attached to sp3 carbon, whereas in aromatic amine, the nitrogen is attached to sp2 carbon. The second factor responsible, which is again very important, that is resonance. Now what you'll find that aromatic compounds will show resonance, and what happens due to resonance, the electron, a pair of electron on nitrogen is taken by this benzene ring because of the resonance, and because it pulls electron, the lone pair of electrons is not easily available to donate, and therefore the base becomes weaker. If aromatic bases are generally weaker as compared to aliphatic bases. So you can see here that there is a lone pair of electrons. This green is a lone pair of electron, and when it undergoes resonance, it is not available. It is taken by this ring, and stabilization of this lone pair of electron keeps this nitrogen electron deficient, and therefore decreases the basic strength of aromatic amines. That is, aniline, nitrogen shows resonance delocalization of lone pair of electrons. Therefore, makes it less basic. Then stability of an ion after when your amine reacts with water produces a conjugate acid. How this conjugate acid is stabilized? If it is more stable, then this particular amine will be a stronger base. So stability of ion, that is the conjugate acid formed from the base, also decides the strength of base, and it is found that if it is stable, the base will be stronger. So these are the factors. Let us see some examples and understand that how we decide the basic strength. For example, guanidine is a strong base. Now you can see in guanidine we have 3 nitrogen atoms. One is attached to sp2 carbon and remaining 2 are attached to NH2. Now each nitrogen has a lone pair of electrons, and this lone pair of electrons after protonation, that is the conjugate acid formed of guanidine, is highly stable. You can see now there is a protonation of this nitrogen, and now it can be stabilized because you have one nitrogen here, other nitrogen here, each has a lone pair of electrons, so they can be used for the stabilization of this ion. And this is how I can show the resonance stabilization or conjugation. And since the conjugate acid form is stable, guanidine becomes a strong base. Now, the basicity of heterocyclic compounds we'll talk about. Pyridine is a moderately basic in nature. It has aromatic character. Pyrrole is a very poor bronze-state base because the nitrogen lone pair is in resonance, and it is used for the aromaticity of that particular molecule. Take this example of pyrrole. Now this lone pair is there, but this lone pair is in conjugation with these double bonds, and in order to get aromatic character, this lone pair has to be with this molecule. It cannot be donated, and because it becomes a poor donor of these electrons, it is less basic or almost neutral. This is your pyridine. Now pyridine also has a lone pair of electrons, but it has already 6 pi electrons in its ring. Here we had only 4 pi electrons. So to have aromatic character, it requires 6 pi electrons. Therefore, this lone pair is in conjugation, so it is pulled in the ring. But here now, this lone pair is outside the ring. It is not involved in conjugation. Therefore, pyridine can easily donate its lone pair of electron, and therefore pyridine is more basic as compared to pyrrole. So pyrrole is weakly basic with pK value minus 3.8, whereas in pyridine, since it is no doubt lone pair electrons, is in the sp2 carbon hybrid orbitals, and does not but take part in the aromaticity, and therefore can be donated, therefore makes it more basic as compared to pyrrole. So pyridine is more basic as compared to pyrrole. Let us see these examples now. First example, you have a para-hydroxy aniline, second para-nitroaniline, and third one we have a ortho-substituted aniline. All these are aromatic in nature, but depending upon what kind of group is attached, their basic strength will be different. For example, in first case, you have a hydroxyl group which is an electron donating group. If you have an electron donating group attached, then the basic character of that molecule will be more. So what you'll find that this compound will be more basic. If I go for the next, we have a nitro group attached para position, and we know nitro is a strong electron withdrawing group, and because of that, the electron withdrawing nature of this NO2, the lone pair is pulled towards nitro group. It is not easily available to donate, and therefore para-nitroaniline is a less basic or weak base. Then another example here we have. Now here what happens, When you have some substituent at ortho position, here resonance may be there, but along with that, a new factor is added, that is steric factor. And because of that, the basicity most of the times of the amines decreases, but sometimes it also increases when it's electron, and this effect is called as the ortho effect. So anything ortho to the amine will decrease the basicity of the aromatic amine, and this effect is called as ortho effect. Because of this steric effect, the basicity decreases. The protonated amine will have greater steric interactions with the ortho group, so that the conjugate acid formed will be less stable, and therefore ortho effect will make that particular base weakly, less basic or weaker. Let us go for the next. Amides are almost neutral in nature. Now in amides, that is in general we say it is RCONH2. Here NH2 group is there like primary amines, but it is attached to a electron withdrawing carbonyl group. Now this electron withdrawing group withdraws electron by conjugation, and you can see now after conjugation, now no more lone pair is available on this nitrogen to donate, and because of that, this amide-like species are neutral in nature. Similarly, just now we have spoken that if you have electron withdrawing group like nitro at para position, you can see here this lone pair is in conjugation, it goes to ortho, then it comes to para, and again it goes to ortho. But when it comes to para, this nitro group pulls this electron towards itself and making this particular compound less basic. So para-nitroaniline is poorly basic in nature. Its basicity is less as compared to aniline because of the electron withdrawing resonance effect of this NO2 group. Let us go for the next. Now there are various aromatic amines we are going to discuss about. Now this particular aromatic amine, that is 2,4,6 trinitroaniline, it is also called as TNA, that is trinitroaniline. It is also called as picaramide. Now picaramide is almost neutral in nature. Why? Because here now we have 1, 2, 3 electron withdrawing groups, and because of this electron withdrawing effect, obviously it will be poorly basic in nature. Then we take diphenylamine. Now in diphenylamine, if I compare with aniline, let's say, we have one ring which will withdraw electrons from nitrogen. Now here you have two rings. This lone pair of electrons of nitrogen will be in conjugation with this ring as well as this ring. So there is electron withdrawing effect because of this ring makes it poorly basic in nature. So diphenylamine is weaker base or less basic as compared to aniline. Let us take this another example now. Now this is your N-dimethyl 2,4,6 trinitroaniline. Surprisingly, this is more basic as compared to these other compounds or these other molecules. Now why it is so? So you'll find that this particular is highly crowded molecule. You can see two nitro groups and N-dimethyl group. They are very close to each other. Ortho effect will be there. So there is a loss in planarity. This particular group moves by 90 degree, and because of that there is a loss of planarity. The lone pair is not in conjugation with the ring. Because it is not in conjugation, it can be donated, and therefore this particular amine, even though it is highly substituted, becomes more basic in nature. If I compare this with 2,6-dimethyl aniline, it also known as xylidine, 2,6-dialanine is weakly basic. Why? Because here now again bulky groups are there, no doubt these are the electron donating group, but still that is less basic as compared to this. Why? Because the lone pair is in conjugation with the ring. It is the electron pair is taken by this particular ring and therefore not available to donate. Here there is a loss in planarity. It is not in resonance, and because of that this particular compound becomes more basic as compared to xylidine. So these are the various factors on which the strength of base depends. Now let us go for the concept of pKa and pKb. Any acid HA, if I take, according to Arrhenius, HA dissolves in water, produces A minus anion and H3O plus cation is formed. If I apply a law of mass action to this and write down the equilibrium constant for this acid, which is weakly acidic, we have shown equilibrium here, it is not a strong acid. So Ka gives concentration of H plus into A minus divided by concentration of Ha. Either you write like this, or you can write it as concentration of H3O plus into concentration of A minus upon Ha. Either you mention it as H3O plus or H plus, does not make any difference. This is how mathematically we write the equation for Ka, that is dissociation constant of weak acid. And then what is pKa? So pKa is a negative logarithm to the base 10 of Ka. So generally the value of Ka will be 10 raised to power something, 10 raised to minus 4, 10 raised to minus 5, something like that. Whereas pKa will be 4 or 5. So pKa values are easy to understand, easy to remember. So therefore we generally convert Ka scale into a pKa scale. So what you'll find, higher the value, lower the value of pKa, stronger will be the acid. If the value of pKa is large, then the acid will be weaker. So this is how we define pKa, just now we discussed, and the pKa value is negative logarithm of Ka to the base 10. So see here, Ka values here, these are the various Ka values written, and corresponding pKa's will be in this manner. So if pKa is less, it's a strong acid, and if pKa is large, then it is a weak acid. So just now we have seen how to write Ka, how to write pK, and what is the relation between strength of acid and pK value. So let us take one example and understand how do I get the value of pK from Ka. Let's say acetic acid is there whose Ka value is 1.8 into 10 raised to minus 5. Then pK is negative logarithm of Ka to the base 10. So negative logarithm of Ka is 1.8 into 10 raised to minus 5. This will become 5 minus log of 1.8. So 5 minus log of 1.8 is approximately 0.26. The value comes to 4.74. So pK value of acetic acid is 4.74. Phosphoric acid, which is a triprotic acid. Now what is triprotic? In general we call it as a polyprotic, but to be more specific, it is triprotic acid because it has got 3 hydrogen which can be donated. It ionizes thrice. How? This H3BO4, first ionization gives 1 H plus ion. Then the anion formed has hydrogen which can further be donated. Second hydrogen ion is given, and this particular anion still has hydrogen, so third time it will dissociate to produce H plus ion. So like this, 1, 2 and 3 hydrogen ions are given. Therefore phosphoric acid is a triprotic acid. Now since it ionizes thrice, it has 3 pKa value. Let us call them as pKa1, pKa2 and pKa3. So what you'll find, all the values are not same. The pKa1 value is 2.16, pKa2 is 7.21 and pKa3 is 12.32. So you can see the first ionization is very easy and makes it strong with acid, but as second ionization becomes difficult. You know why? Because already it is electron rich, and then losing proton will be difficult for this particular ion. And after that again it gets 2 negative charges. It becomes very difficult to lose proton, and therefore the pK value goes on increasing. So the relation between pK and pKb. Now what is pKb? So use your logic now. If pKa is a negative logarithm of Ka to the base 10, pKb for bases, it will be negative logarithm of Kb, where Kb is the dissociation constant of base, Ka is the dissociation constant of acid. From the pH scale, we have determined that the value of pKa plus pKb will be equal to 14. If higher the value of pKa, the base will be stronger, but acid will be weaker. Most of the alkyl amines, the pKa values ranges from 9.5 to 11, making it highly basic. the lower pKb values will be indicating the strong base. So pKb is negative logarithm of Kb. If I have a base BOH, then it ionizes to give B++ OH minus. And then I can apply the law of mass action to find Kb, that is dissociation constant of base, as concentration of B plus into concentration of OH minus upon BOH. So this is how we represent the equation for Kb, and the pKb is written as negative logarithm of Kb to the base 10. So I know when pH is equal to pK, the strength of acid will be equal to strength of base. When pH is less than pK, then it is protonated form. And when pH is greater than pK, then it is a deprotonated form. So this is how we give the correlations. Then it is generally observed that when we talk about strengths of bases, this is your ammonia, this is your primary amine, this is your secondary amine, and this is your tertiary amine. If you see their pKb values now, 4.79, 3.37, 3.02, and 3.35. What is the relation between pKb and the strength of base? Lower the value of pKb, stronger will be the base. So ammonia, primary amine, secondary amine, and tertiary amine. Among this, 3.02 is the least value. That means secondary amines are the strongest bases. Then you have your tertiary amine, then you have primary amine, and then ammonia. All amines are more basic as compared to ammonia. This is because in all these amines, one or more alkyl groups are attached to nitrogen, and this alkyl group will stabilize the conjugate acid formed after protonation due to inductive effect, that is plus I effect. Therefore, they will be stable. But this is not the only one factor. The second factor is hydrogen bonding or steric effect. More the number of hydrogen atom attached to this nitrogen, more will be the capacity to form hydrogen bonding with the solvent like water, and that will make that particular molecule, an ion or the conjugate acid, more stable. Along with that, a steric factor is also there. So why in tertiary amines, actually there are three alkyl groups attached. So the conjugate acid of this amine should be most stable as compared to secondary amine. But it is observed that it is not the case, because in tertiary amine, we have got three alkyl groups, bulky groups. Therefore, there is a steric interaction. As well as it does not have any hydrogen atom in that to form hydrogen bond with the solvent molecule. Both makes the conjugate acid less stable as compared to conjugate acid of the secondary amine, and therefore secondary amine are the strongest bases when I compare with tertiary or primary amines. All primary, secondary, and tertiary amines are stronger as compared to ammonia. So these are the various acids, and these are the various pK values. We can always talk about their acidic strength, increases, decreases, and what are the various factors. Go back, revise it, as well as you can see here the scale is given, Kb value, Ka value is given, so you can always find out their pK values and verify whether it is stronger or weaker base or weaker acid. So all these formulas just now what we have discussed are helpful to find out pK, pKb values of corresponding acids and bases. And from these values, we can always discuss about whether the acid or base will be strong or weak. With organic acid, we have seen that inductive effect, mesomeric or resonance effect plays very important role. They affect the pK values. Water is therefore more able, water is generally used as a solvent, helps to stabilize the anions, as well as it some polar solvent like DMSO also do the same thing, but hydrogen bonding is possible with DMSO like water. So with this, we come to an end of this particular module. These are the various questions asked based on what we have done in this particular module. try to write answer for them, and try to justify your answers. So with this, we finish with this module. Next time we'll be talking about module number 3, where we'll be discussing the various comparative aspects, as well as we will be talking about the um, acid-base catalysis, and some problems will be solved.